it coming up? No, it's not coming up, of course, because I have to plug it in. There we go. Okay, so today we're going to talk about normal loading some more, and then we'll get into torsion. That will be session 9. And for normal loading, we're going to talk about finite element analysis, and we're also going to talk about how to think about thermal strain and stress. But first, okay, there were some questions about the homework, and in particular, we were looking at this problem, right? Okay, and the question is, how do we figure out the effective spring constant, okay, between F and delta, right? So we're looking for K, which is going to be F over delta, correct? So in the last session, we went through the 3 columns, the constitutive, the geometric compatibility, the equilibrium, or equilibrium on the left, okay? There's actually a simpler way that uses a little bit of a trick, okay? So if you still have a question about how to do this, you can go back and look at how we did it last time. But one trick is to think of this as a network of springs. Like this. Like that. Okay? And let's call this K1 and we'll call this K2. Alright? Now, we only have kind of 2 guesses, right? They're either springs are acting in series or parallel, correct? In this case, is the force the same in both springs? You can be bold. You said no, it's not. Okay? It's not the same, right? If we were to think about this just in terms of the basic binary answer of one is in tension, right, and the other is going to be in compression, most likely. Okay? So the forces are not necessarily the same, okay, in terms of them, having this attribute of one being in tension, one compression. Are the displacements the same? Yeah, right. The one you could argue one's in compression, one's tension again, but yes, they're going to be the same magnitude. Okay. Now, you could argue that the forces potentially could be of the same magnitude too, right? But that would require that the spring constants be the same. The spring constants are not necessarily the same here because in this problem there was an L1 and an L2. Okay. The cross-sectional area is the same. The elastic modulus is the same. Okay. But if the lengths are different, then the spring constants are going to be different. Does that make sense? Why is that? Do you remember what we have, right? The general formula, I'm just going to write, instead of delta, I'm just going to write displacement is equal to this PL over EA, right? Normally I write delta, but I've got a delta over here, so I'm not going to write delta. And if I want the K, right, the K here, the constant, we'll call it the rate, okay, right, then that would be F over delta or P over delta, right? So P over delta or P over displacement, right? That gives us EA over L. Okay? So if E is the same for both and A is the same for both, but L is different, then we have different spring constants. Okay. So what do we remember? Springs in parallel. Displacements are the same, right? And forces are not necessarily. Okay? And this is the configuration that we're familiar with. Right? Does that look right to you? Okay? So the force could be distributed differently between those two springs, but the displacement of those two springs is going to be the same. Okay. Springs in series, all right, we have the same force in each of them, but their displacements are different. Okay. So in this case, it's a little tricky, but you can actually do a little flipperoo. Alright, and if you flip these around, look what you get. Do you see that? Imagine I take this wall and I just rotate it around so that it looks like this. It's still opposing, right? It's still opposing the motion. Is it not? Right? In this case, it's applying a force, K2, the spring 2, is applying a force to the left side. Okay? And it's proportional to the displacement. So even though these are written as if they're in series, because of the way we have the force and the displacement, they're actually acting in parallel with each other. So if that's the case, then the problem becomes a little bit simpler, right? That's the delta. What is now the K for this system? Yeah, that's it. Right, and what is K1? K1 is going to be EA over L1. K2 is going to be EA over L2. And so you saw in the group meeting last night, I said, take a look at the exam, I think, from the spring of 2023, so a little over a year ago. And I didn't give that much of an explanation for what was in there, but the answer was there, right? It was just this. It was it was EA over L1 plus EA over L2. Okay? So if you didn't get it the other way, this way is simpler and should give you the same result. Any questions on this? Yes, Andrew.
If the bar is like made of like the same material, can you, instead of doing L1 and L2, just combine the whole length as L1 plus L2 and then use the equation K equals EA over L?
What do you think? That's a different.
I thought so.
You thought so, right? And you sent me the message, and what did I say? Okay, so what you're saying, what you're asking, okay, is, can I think of the spring constant? Is the spring constant, okay, so let me just do this in a different color. Is the effective spring constant what did you say? You said EA over L1 plus L2. Is that what you asked? Okay. What do you all think? first off, you realize it's not the same as what we have over here, right? So that's not. What does this spring constant describe? If you were to draw the picture, what does this describe?
Spring constant of like the whole bar.
That's right, it is. It's the spring constant of, this is, what you just described is this. Okay, assuming that this has got a length L1, this has a length L2, and this is EA, and this is EA. Okay. That is what you've got, right? But that's not the configuration that we have on the line. This is good, right? It's good. You want it to be this. This would be the nice way to do it. And this goes back, remember when we were talking about bars as springs initially? This goes back to that, like, kind of early session, I can't remember which one it is, where we said, look, if I put two springs, right, in series with each other, if I double the length of the bar, right, that will do what to the spring constant? It's going to decrease it by a factor of 2. Okay, so this is exactly that. Now with a little bit more understanding, because we've got flee, and in fact, if you even go further, like to what we discussed last time, we have the integral of p over EA dx, right? And that's how you get flee, or that's how you get flee. Okay? Yes.
Can you explain one more time why the springs are technically working in series? Is it because the force isn't being pulled from the end?
Wait, so while they're in parallel, yes.
Yeah.
Okay. Let's just say I get rid of this thing. Okay, so we agree that this spring is exerting a force, and then minus, if this were x positive, right, it's going to the left, right? When I pull to the right, this spring is going to be pulling to the left, correct? Okay? So if we covered up this, we're okay with K1, right? Right? This is exactly acting like that is there. Okay, the question is, what in the world's going on? Now let's cover up this one over here. Okay. If I am now just looking at this spring, right, and I'm applying a force to the right on the second spring, do we agree that it's also going to be pulling or pushing to the left? And do we also agree that it's also pushing or pulling to the left proportional to delta? And do we agree that it's also experiencing the same amount of both of these springs are experiencing the same amount of displacement? Although like one's being compression and one's tension? Well, that's what this describes too. Okay? Yes?
So the K that you got without the subscript, what does that represent? Is that the K with the whole?
Yeah. So we're looking for the K is equal to F delta at the very top. Alright? That's why I didn't write delta over here, because I was just trying to make that a more general. But we're looking for the delta, we're looking for the effective spring constant. I could have written K subscript effective, right? And that's relating this out to that delta.
So that's the spring constant at that specific point?
That's right.
Okay.
That's right. Right? So, I mean, I can look at it a couple of different ways. I could say, I've got my nice physics system where I've got two springs. Now, this spring this is assuming, right, that this spring can handle compression. If I put like my nice physics spring, like just the coils, and I don't have pretension, I would have to have pretension essentially, okay? Or you know, if there's no pretension here, it's just gonna buckle, right? But it turns out that this is a bar, so it can handle compression. Okay. Good. All right, or I hope it's good. All right, so what we're gonna do now is hope that I can get this to work. They updated the software, and I'll be honest, I was having a little bit of interesting moments, okay? But we're going to demonstrate how we can use finite element analysis to do some of the same problems we've been doing with the bar. Okay, so this is like, how do you say it? It's not cheating, but it's trying to do this without knowing mechanics or knowing what we've covered, okay? But we want to know mechanics to be able to verify what we're simulating. So what we're going to do is we're going to attempt to make this bar, okay, in 3D, in CAD, very simple. It's just essentially an extruded square, okay? And we're going to then fix the left side or one side, and we're going to apply a pressure that's represented by this force over the right side, and we're going to see what the resulting stresses and strains are. Okay. So if you want to follow along, if you brought your computer, you can. Otherwise, we'll have fun. So you're going to want to install something called FreeCAD. Now, well, I think you're going to want to install it, but of course, if you want to do this with SolidWorks, you can. Okay? Not the finite element. Okay, so what I want you to turn in is screenshots. You should turn in or submit screenshots in MechMat. Okay, not SolidWorks. I understand SolidWorks doesn't submit finite element. Okay, I want you to do this using this other software. Okay, and FreeCAD I think works on a Mac as well. All right. Unfortunately, MechMat, as far as I know, only works in a PC. On a PC. Okay. So you could use the lab machines, or you can. I'll show you how to run that in a minute, and it's not that hard to run as long as you have a PC. So if you have an old PC at home lying around, you should be able to run it. Okay. So what we're going to do, this should come up more or less something similar when you open up FreeCAD, and this is probably an older version. The Pre-Pro-Max that I downloaded is the current one, but the FreeCAD may be a little bit older. But anyway, we're going to create a new, so you just click Create New, and then nothing happens, and you're like, what's going on? So then you come up to this, I guess it's a workbench selector, and we're going to go to part, not part design. Part design is useful for extrusions and stuff, but actually we're going to use an even simpler building block here. So we're going to go to part, you click on part, and then we click on this cube, and it creates the solid cube, and then you click on cube, and then you see that it has dimensions for the cube. And in the slides, all right, we're going to say the length is 5 centimeters. The A and B it's going to be a square cross section of just 1 centimeter by 1 centimeter. Okay, so for that, we're going to we'll say the length is 50 millimeters. Okay, and then it's 10 by 10. Right, so that's what it should look like, more or less. Okay. We're going to then export it to STL, so you can save it if you like in its native format, but for now I'm just going to export it, and you can see I have some other ones, so we'll call this bar sample with an STL. Okay, now remember 50, 10, 10. Now what you're going to do is you're going to open up, let's see, where did I put it? Well, maybe so if you go to the website for Pre-Pro-Max, okay, you're going to download the zip file. So I guess I'll just delete this just so that, well, I don't have to delete it, but I can. All right, so it's a zip file, so if you're not familiar with zip files, they are compressed files that you can extract. So you just extract it, and it will go ahead and place it here. And we don't even install this software. We just run the executable. And Windows usually throws up, are you sure you want to do this kind of message? then once we've opened up pre-Pomax, so now it's created this new folder. Okay, right, so it's got this new folder here. And we double click on it, and then we can just run it. Like so. Yeah, so here's the message it says, so you click on more info, and you say run anyway. At least I do. Okay. All right, so now this is the interface, and it might be a little bit small. I don't know if I can make the words, I don't know if I can make them, maybe I can make the lettering a little bit bigger. Graphics, I haven't actually done this. Legend, general. I don't see how to make it the lettering bigger. Okay, but there's probably, I don't know, there might be a way to do it. But anyway, we're going to do new, so you have to do new first. So you do new, and we can go ahead and we'll go into meters, kilograms, seconds, Celsius. All right, and we're going to do 3D, and we hit OK. All right, and that's the length scale. That's enormous. All right, and so what we want to do is make sure that that length scale reflects the size, the actual size of what we created in CAD. And whenever you do these, if you do it in SolidWorks or you do it in some other piece of software, you want to make sure that it brings it in appropriately. Okay, so we're going to import now what we just created. So we call it a bar sample. Okay, and we bring it in. All right, and look at that. It says it's over, and I'm using, so shift and middle button moves it down. It says it's over 30 meters long. We only want it to be 5 centimeters long. All right, so it looks like it's 50 meters long. And if we want it to be 5 centimeters, what's the difference in the factor? We go from 15 meters to 5 centimeters. What scaling factor do we need? 1,000, right? Okay, so we're going to come over here to geometry, and we're going to go to the part, and we're going to hit transform, and we're going to hit scale. And then we're going to use our scaling factors here as 0.001 in X, 0.001 in Y, 0.001 in Z. Okay? And then we're going to hit apply. And it disappeared. Why? Well, it was shrunken by 1,000. So then we can go to view, and we can hit zoom to fit. And what do we know? And so like standard view, let's do a front view like that. Okay. Shift middle button. That looks like about 5 centimeters. Okay. So now, and then maybe we should, you know, if we rotate, so middle button, we rotate, right? And we bring it over here, and we rotate a little bit more. All right, yeah, okay. And it's not doing exactly what I want, so I can do a top view. Woo! No, that's not what I wanted. Let's do a left view, right, like that. Yeah, so that looks like it's about 10 millimeters, okay, or 1 centimeter. Okay, so now we've got our part, and we want to do, oops, let's bring it like this, let's like that. Okay, so we notice that we have, if you see this, right, this is X, this is Y, and this is Z coming out this, kind of this way-ish. So here, now we can come and we can work on a mesh setup, and we can click on mesh parameters, and we're going to mesh this part. Okay, so we click part, and then we click on this. Okay, and let's see what it does for the max element size. Okay, let's see, that should be probably okay. And we hit OK, and then we hit mesh. Create. Oh, that's the mesh setup. Let's see. Just create. Nope, we don't. Okay, we have to go over here where I don't know how to do this. Create mesh up here. Okay, that's not too bad. That looks okay. All right, but maybe you can also refine it a little bit. So maybe it should refine it. So I can go to Edit, Undo, Create Mesh. I can come into the mesh parameters, and let's say that I don't know. Let's just say that we're going to make it down to like 1 millimeter. Okay. Hit OK. Hit Mesh. Hit Create Mesh. Takes a little bit longer now to get all these elements. In fact, okay. So you see now that's a more refined mesh. All right. So why is this called finite element analysis? It's called finite element analysis because you have a finite number of elements that you're putting into your part. Okay? And in reality, these are like interesting. They're three-dimensional. We're only kind of seeing the surfaces here on the edges, but they're three-dimensional elements that go into the part. Okay, so now we're going to go ahead and we're going to create a section, and we're going to create a solid section. I forget to do this like all the time, okay? So I'm going to go ahead and we got to make sure that we have a solid section, and we hit OK. There's no material defined. Okay, so first we have to define the material. All right, so fine, we'll define the material. So see, I forgot the order. So we go to Elastic, and we click this arrow, and brings it over. And in the slides, we said that we're going to use elastic modulus, a Young's modulus of 200 gigapascals, and we're going to use a Poisson ratio of 0.3. Okay, so let's come back over here. You can do 200 gigapascals like that, and it puts it in for you, and Poisson ratio is 0.3. You can also do like 200 E9 if you like. So we'll hit OK. So now it has that. Now let's see if we can create a solid section. All right, it's going to be a part. I click on that part, and then I hit OK. All right, so now I've got a solid section. Here, then, we're going to come over here to this thing called steps, and we're going to create a step. We're going to be doing, so it has different types of modeling you can do. We're doing statics. Okay, so that's what it's called the step, right? So you could have like something. You can do different types of stuff, right? So we're going to do static step, and we said okay. All right. Now boundary conditions. Boundary conditions, right? Those are what? Well, let's see. Let me tell you what I want to do. I want to put the load that I'm applying, this pressure, I want to put on this side. Okay. But if I pull on this side, I got to make sure that I've got something keeping the structure from going somewhere, right? I need a wall, right? So what do? I come over here to my BC, and I'm going to create a fixed, all right? And I can do this on a surface, all right? So let's see if it will work. Yep, it allows me to select that surface. I hit OK. All right, now that surface is fixed, all right? That doesn't exactly look like the wall constraints we use, okay, but that's a wall constraint. Right. And then on this surface, I can put a load, this surface over here, right? So I can create a load. Now, what I'm going to use here is a uniform pressure, all right, on the surface, like that. I hit OK. Oh, I have to put a magnitude. All right, so now the question is, what is the magnitude? Well, I go back over here. Okay, they said 1,000 newtons, okay, or on a 1 centimeter by 1 centimeter surface. Okay, that turns out, okay, if you do it, right, 1,000, so 1 centimeter times 1 centimeter, that's 0.01 times 0.01 meters, right? So that's going to be 10 to the minus 4 meters squared, okay? And so I've got 1,000 divided by 10 to the minus 4, 1,000, 10 to the 3, right? And plus or minus minus 4, so I'm going to have 10 to the 7, okay? And that is 10 megapascals, right? So 10 times 10 to the 6th. So now, we come over here, and we put in 10 MPa, like that, okay? And we hit OK. And what's it going to do? It's going to put it in the wrong direction. Yes, it put it into. So that's just the way that they do it. So what do we come in and we come back and we edit it and we put a minus sign. Like that. All right? So at this point, we've put our constraints, we've got our elements, or put a constraint on this side, we've got our elements, and we've got a force on the end. So we can then go over to analysis and we can click run. And it's going to think and think. Yeah, my computer has got a lot going on right now. Okay, so it took 18 seconds, and then we can click on results. We can open this up, and what we see is this is where we were. It was an FE model on this tab, and then we had geometry. That was what we started with, FE model. Now we have the results tab. Okay, and this this display, all right, for under results, has a few different tabs. So one is this, which is going to be displacement. All right. So it's showing us colors based on this, on how much things are displacing, and it's all displacement, right? So this is going to be the magnitude of displacement in X direction, Y direction, and Z direction. Okay. Is there much displacement in the Y direction? What do you think? This is Y. Which direction were we pulling? Yeah, we're pulling the X, right? So there shouldn't be much displacement in Y. There shouldn't be much displacement in Z. There should be mostly in X. But right now we're showing all the displacement. So this is the magnitude, right? So you see, here it's telling us that the max is about 2.5 times 10 to the minus 6 meters. So that's about 2.5. Even so, right? This maximum displacement is only 2.5 microns. So it's still pretty small, right? That's the maximum. That's overall. But it's going to be even less in Y and Z than it is in X. Okay. So now we go to U1. U1, so what is 1 as a subscript, right? That's the X direction. 2 is going to be the Y direction, and 3 is going to be the Z direction. Right? So when we see these other subscripts, okay, we're going to have U1, U2, U3. These are all displacements. So like we said, U1 is pretty much identical in terms of the max. It's identical to all. Like you can see there's just like a change in the third decimal place. Very slight. Okay, and maybe it's not clear. It's telling us that the max displacement is here at this bottom corner. Right? In reality, maybe it's around here. I don't know, whatever. Okay, but you see that? Because this is displacement, and it's also illustrative because, yes, I applied a stress here, but imagine that this were a spring, right? We've talked about this. This part over here is going to be displacing less than this part over here because there's a lot more length to it. Right? Delta is equal to phi. Okay, but let's get to the things that we're maybe more interested in. So one is, whoa, what is this now? Okay, so this is telling us what the stress S11 is. That's sigma 11. That's sigma 11. That's sigma 1. All right, so that's the stress on the X face in the X direction for every single element in this system. Why in the world is there a lot of stress over here on the left? Why? Why is it not just beautiful? Like, you know, I can look, so we'll talk about Mises, which is like an equivalent stress, but why is there a lot of stress over there? I can, all three directions, there's a lot of stress relative, okay, over there. What's going on? Any ideas? What could be going on? Yes.
Could be that, it's just a wild guess, but it's not very ductile, so all of the stress is kind of
Okay, not very ductile, alright. Why would there be stress over there? Yes?
Oh, gosh, so when you would pull something away, the end that's not getting pulled is bigger, because the part that's getting pulled is smaller.
Yeah. Right, awesome. Okay, so what did I do on this left side? I said it is fixed. Everything is fixed. Fixed x direction, fixed y direction, fixed z direction. Okay? And it turns out in these models, so there are ways we can get around this, okay, to make it look more idealistic. For example, you can fix one point, and then you can only fix one point on this model, on that left side, and then have just displacement be restrained in the x direction, or in the x direction, because that's where you're pulling. Okay. But what's happening is the Poisson effect. Poisson's ratio is saying, I want to shrink there. And that constraint is saying, no way, I'm not letting you do it. Alright? And because of that, there's a tug of war in the y and the z directions. Okay? And that's causing a stress that we see also in the x. Okay, for the Poisson ratio. Okay? So, now, so this max is not very relevant to our problem, okay? Because this is not the ideal scenario, which is what we've been modeling. Okay? The ideal scenario is that we have a nice uniform force and we're interested in the stress. Okay, so what would the stress be? Well, the stress is kind of trivial. We decided that we're going to apply sigma x of 10 megapascals on the end. So what we better see, or what we hope to see, is 10 megapascals. Right? Now, maybe I'm wrong, okay? But that's what I hope to see. So if we come back over here, and now you just click. So I'm going to click like over here. Or actually, I'm going to right click and I'm going to do a query. I'm going to do, right here, vertex node. Now let's pick that one. What do you see? What is the value there? It's 1 times 7 is 7. That's 10 megapascals. All right? So it tells us that, okay, sanity check. All right? Now, what's the other thing what we want to calculate? Let's figure out the strain. Okay? Okay, it's the strain. So how do you calculate strain? Well, you say epsilon x is equal to 1 over e times this thingy bob. Right? Sigma x minus nu times quantity sigma y plus sigma z. All right? So that's great. What are sigma y and sigma z? 0, right? So this is just going to be nice Hooke's law, essentially, in the x direction. So it should just be sigma x over e, which should be 50 times 10 to the minus 6 by this calculation. So now we go over and we say, all right, I really want to know the strain. Well, strain is going to be given over, not in the stress category, but in this strain category, all right? And epsilon, and if I want epsilon x, it's really epsilon 1, 1, right? So now I click on epsilon 1, 1, okay? And what what do I get? 5 times 10 to the minus 5. It was 50, right? We said it was 50 times 10 to the minus 6. Boomba, right? We're on fire, okay? We're getting the right results, okay? Now, more complicated is the strain in the orthogonal directions. So for that, right, we have this. So remember, if we have epsilon y, this is 0. This is the sigma x of 10 megapascals. This is 0.3. All right. So now what we should get is about minus 15 microstrain. Okay. And epsilon z should be equal to epsilon y. So, oops, that's recad. Okay. So now if we go to epsilon e22 or epsilon y, boom, minus 1.5 times e to the minus 5. And then epsilon 3 or epsilon z, boom, minus 1.5 times e to the times 10 to the minus 5. Right? Isn't this cool? Maybe, maybe not. All right, but this is what we should do before we make more complicated simulations. What do I mean by this? What is the this? This is the baby set. Right? If before I simulate a chair or the fuselage of a plane, okay, I want to do kind of a baby set, a dummy check, right? I want to make a model where I can get a result and compare it to my analytical calculations. Okay? This class is going to teach you a whole bunch of fundamental analytical calculations, but you're never probably going to be asked to make a bar. Okay? Maybe you will be. Maybe actually, if you go into manufacturing, which is an excellent area of engineering, you probably will be making a lot of simple shapes. But you've got to get the tolerances right. Okay? And you've got to get the material properties right. And it's super complicated to do that. And it's super interesting. Okay? But yeah, in many cases, you're going to see beautiful pictures with finite element analysis. Just look at YouTube. All right? Look at what we do in multiphysics simulations if you're bored. All right? We have some videos on that. You want to make sure that these values that you're getting match reality. And so part of the power of this course is explaining how we get those fundamental results. All right? So your homework is going to be doing exactly what we just said. Okay? You're going to be putting in different dimensions. And what's killer about this, all right, what hurts, okay, is that if you get it wrong, you got to start all over again. Right? So let me please, okay, before you put your answer here, run the analytical calculation and compare it to what you got in your simulation. If they do not match, don't enter it until you get them to match. Okay? Because you can just get them. You can get it. They'll throw you another query, and it's going to give you different numbers, and you're going to have to start all over. It's not the end of the world. Okay? But you get what I'm saying. Make sure that this number matches your analytical result. Okay? Because this was is being calculated in Canvas, not because it's running an FEA, it's because it's using the analytical result calculations. Okay? And then, so the first question is going to be, what is the axial strain along the length of the bar in microstrain? Okay, so make sure you multiply by 1 million, by 10 to the 6th, and along the length of the bar, if you do it the way I just did it, that would be E11. Okay. The next question is, what is the strain in the direction of the height of the bar? A strain in microstrain. So height was y, I think, or z, right? They're going to be the same, but I think it was y, if that would be thickness. So use either epsilon or e22 or epsilon y, right? And calculate stuff. What happened? Why is this happening? This is happening because of the Poisson's ratio. Is it negative or positive? It's negative. Okay, so make sure you get that as well. Okay, fun. Okay, so now let's go on. We're going to talk about thermal strain and stress. Where in your high school math or science or physics or whatever did they tell you about the thermal coefficient of expansion? Or maybe in college? Did they ever talk about this? Okay, where did they teach you this stuff? Huh? Okay, great. Alright, so what is a thermal coefficient of expansion? What do you remember? What do you think it is? You can read the slide, right? But what is it essentially? In your own words. Isaac, what do you think?
This is like when you don't find the change of length.
When you what? When you what? Sorry, I didn't hear it quite.
Like you don't find the change of the length of the. So we deal with. Is it deal with two bars, like two different type of springs?
Okay, so sometimes, yes, so that's a classic question. We won't analyze that here, but that you have two metals right next to each other with different coefficients of thermal expansion, and you heat up the system, and one expands more than the other and causes there to be curvature. So that is kind of a classic mechanics question, but I'm not asking you that. Okay. In your someone else, just what do you think this is? What is a coefficient of thermal expansion? Just in everyday terms, yeah.
I guess it helps define the rate of expansion as the material expands.
Yeah. So it explains how much something expands when you heat it up. That's pretty much all it is, right? And it's based on temperature. So it's like if you increase it by so many degrees Kelvin, so many degrees Celsius, so many degrees Fahrenheit, this is how much volumetric expansion you expect. This is how much linear expansion you expect, right? And we are more concerned with the coefficient of linear expansion. Okay? So we're typically thinking about how they how you have a bar, right? And if I multiply by this coefficient of thermal expansion times delta T, so that's a change in temperature, times the length, that will give me the delta length, right? And if I do delta L over L, right, that's strain. So now, I don't know if your physics class told you this, but do they talk in terms of strain? They probably talk in terms of change in length, right? Because that's this equation. But we're thinking now, not only in terms of the change in length of a bar, but we're thinking about how much strain is there in the material, in the structure, based on just alpha times delta T. Okay? Now, if I've got a bar and I heat it up, and it has a coefficient of thermal expansion, and it's a positive coefficient of thermal expansion, what happens to the strain? Well, we just said strain is going to increase, right? It's going to be positive. What's the stress in this bar? If it's only being held, say, at one end, or if I got it like in a tongs, alright, and I'm just holding it because it's really hot. What's the stress in this bar? What do you think? Well, the answer is there, right? That's what we were going to say, Jake.
I was gonna say that
the stress in it is 0. Okay? Because I'm not applying any mechanical force on it, right? And it just has expanded. Now, what you're thinking is, what happens if you have a bar that's stuck in between two walls? Like your creaking house. Okay? You know, in the morning and the evenings, right, you hear everything. At least, well, maybe it's just because we live in an old house, right? But like it's making all kinds of noise because it's things are expanding at different amounts because they're at different temperatures. Okay? And so you have some fighting, you have some tug of war. There you're going to have stresses involved. And there the last hypothesis is going to play an effect. Okay? So here are a bunch of linear and volumetric coefficients of thermal expansion. What is the factor between these? 9, 27, whatever, almost 9, almost 27, right? 10, 30, it's a factor of 3, right? Okay, so if, remember this? We did this yesterday, right? We said that we could have this volumetric strain that we described as the dilatation. Well, it comes out here too. So, yes, I said we think about linear coefficient of thermal expansion mostly for this class, but if someone gives you a volumetric coefficient of thermal expansion, don't take the cube root of it. That would be my temptation. Divide by 3 and you got the linear coefficient of thermal expansion. Alright, what are some big time players in terms of coefficients of expansion? Well, look at this. Gasoline. That's a big player. Petroleum products. They have fairly large coefficients of thermal expansion, at least compared to, let's say, some of the aluminums and the metals. Okay, you see that? So polypropylene, 250, aluminum, 20. Alright? Well, water is 70. So that has a pretty high thermal coefficient of thermal expansion, right? But this is typically what you're gonna see, that the metals are maybe, aluminum has a high one compared to the other metals, but like 10 to the minus 6, or 10 times 10 to the minus 6. I guess I should include that too. What are the units? They're something over Kelvin, or something over Celsius, or something over Fahrenheit. Right? And it's obviously something over Kelvin is going to be the same as something over Celsius, right? But something over Fahrenheit is going to be different. Okay, it's going to be a smaller number because Fahrenheit is a smaller increment compared to Celsius, right? So whatever. What am I trying to say here? The units are important. The reason it's dimensionless in the numerator is because we're talking about strain. Okay? It's alpha times delta T. I need something to knock out the temperature. And that's what the denominator of the units for their coefficient of thermal expansion does. Alright. Right, so that's just relating these two to each other as we said before. Okay. Now, let's say we have an unconstrained bar of length 1 meter and cross-sectional area of 1 centimeter squared with last hypothesis of blah and volumetric coefficient of blah. If we heat the bar uniformly from 20 degrees to 212 degrees Celsius, what is the change in length of the bar? Okay, well there's a collab that you can use, alright, but basically the process is going to be, what is the change in temperature? Alright, and it's given in Celsius, so Celsius, Kelvin, whatever. Right? Offset 273.15 or something like that. they gave us a volumetric coefficient of expansion, 69, so divide by 3, that should be something like 23, right, which is what we saw on the previous slide for what? Well, if we didn't know what material it was that it's got an elastic constant of 70 gigapascals. So that should give us a clue, right, that it's aluminum. And what is just the length, change of length? Well, we take that linear coefficient of thermal expansion times the change in temperature times the initial length, and we get it. So it's something like 4 millimeters. Now, what happens if I will constrain that system between two walls? This is what Shane was getting at. Well, this is where superposition comes in handy, right? We know how to handle these kinds of systems. We say, oh, go ahead. I'll pull, but I'm not pulling this time. I'm just heating. So what do I have to think about? I have to think my geometric compatibility. I have to think, oh, I need to push a certain amount to get rid of that displacement, right? That deformation. So I need to undo. It's a forceful undo. I think Windows undo, Control Z is, it's not so forceful. This is a pretty, we're putting on force. And so if I do that, generally speaking, if I have a bar that was fixed in between two walls, and now I heat up the bar, and the ends of the walls or the ends of the bar do not move, is the resulting force going to be compressing it? Is the resulting stress going to be compressive, or is it going to be tensile? Well, it's going to be compressive, right? Because I'm essentially pushing on it and I'm keeping it constrained. And you get these tug of wars. Let's say that, now you had some type of, if I had a system where, the tug of wars, right? Let's just say that I had some type of fictitious system where I have, let's say this is like some ceramic, okay, which has a fairly low coefficient of thermal expansion. And then I put in this. This is not good. I should have used a different color. Well, I guess I still can. I heat up this bar. All right, and let's say that this is a, I don't know, I would like to use a polymer. So this is the thing, if I use a polymer bar, it doesn't have a very high elastic modulus, so it can't do a whole lot of pushing, all right? So I don't know, let's just say that this is aluminum, all right? And they're different things, right? Well, if this, let's say this has a higher, so let's just say, suppose that the alpha aluminum is greater than the alpha ceramic, whatever it is, silica. Okay? Well, if that's the case, right, then this thing is going to be expanding more than this is expanding. And so that's going to put this in compression and this in tension. Okay, you see that? So these are where these kind of mind games start to happen. Okay? Now the net result is actually that if this whole thing was put in the same, if this whole thing was like put in a furnace, right, and I measure the distance from the left end to the right end of this whole system, the net result is still that it expands, right? Because they're both expanding, but there's going to be a tug of war, or push of war, or push or pull of war with them. Yeah. But this, I guess maybe I was jumping. Whoops. Maybe I was jumping a little bit ahead of the game, all right? Because what we're trying to get here is just look. This is the amount of force I gotta apply to constrain this simple bar, okay? And that bar has an elastic modulus. Oh, what in the world? That bar. What happened? Doo-ba-doo. Okay, well you can see now, right? That bar has an elastic modulus E, has a cross-sectional area A. So I can think of, okay, that delta is phi, right? And so now I have that force associated. I have to balance these displacements, the thermal displacement and the displacement due to compression of that bar. That has to equal 0. So now I can figure out the force, and I can figure out that the thermal stress, okay, is going to be or the stress due to this applied thermal material is going to be just that force divided by the cross-sectional area. And in this case, because I'm applying a force, now the strain is 0 because I've applied a force. It's constrained, although before it was not 0. Okay. All right. This is a classic hard problem, which you get to do on your own. But it's too much stuff. Okay. We're going to show you how to do it 2 ways. And one way is by thinking in terms of like the 3 pillars, right? And the other way is to think about it by using superposition. All right, so let's walk through this. I'm so behind. I should have waited, so I apologize. It's my fault. Okay. So here, and this is kind of like the last thing you want to know how to do before Monday. Okay. I've got one section with an elastic modulus E1, length 1, and cross-sectional area A, and I've got another with E2, L2, and the cross-sectional area A. I've got one section with alpha 1, I've got the other section with alpha 2. So the question is, what are the axial strains in both sections? So with equilibrium, these two are essentially springs in series. You're like, oh no, but we just did what I was in parallel with them next to each other. No. There's no force being applied here at the middle. Remember that? Okay. So that means I don't have a different internal force here between this and this. The internal forces are going to be the same. It's one internal force across the whole thing, and that means that this force on the left end and this force on the right end are going to be the same as well. Everyone buy that? Okay. Now, if this were unconstrained, right, then this would be the total displacement. Right? So that means that if it's constrained, then the force of F1 or F2, all these forces, F, whatever you want to call it, yes, this is like a spring in series, and so it's going to be series times that delta. Okay, the K effective times that delta. All right, so that's a nice relationship for the force, all right, that we can calculate, right? Because now I know that deltas are these, or delta is this, so I can figure out what the force is across the system. Okay. And if I wanted to think about unconstrained, okay, delta 1 and delta 2, all right, so delta 1's what we would say is the unconstrained delta, and delta 2 is this unconstrained this deformation actually. All right, because delta 2 is not this delta plus the whatever would delta 2 is the deformation of this section. Delta 1 is both the displacement to the right and the deformation of the blue section. So anyway, the overall delta is this delta 1 plus delta 2. Okay, so we're making use of, so this was equilibrium, sorry, the three pillars: equilibrium, geometry, constitutive equations. So we made use of equilibrium, now we're making use of geometry, okay, and we have also making use of constitutive equations here, right? Well, this was constitutive equation that we used here, and these are constitutive equations, and these are so we have a bunch of constitutive equations that we already plugged into these other two columns. Okay, so now these are unconstrained displacements or deformations, better said, of these two sections. But what do I have? I have a force that's constraining, that's acting to constrain these. Okay? So we can apply this F or F1 or F2, whatever we want to call it, okay, to these different elements. Okay? And when we do that, we can think of the combined strain of what's happening in the first section and what's happening in the second section. Okay, so first, we agree that these are the thermal strings, right? Alpha 1 delta T. That's a typo. Okay. Alright, because these are the thermal displacements. These are multiplied by L, but this should not have an L there. Okay. So those are the thermal strains, and the force-based strains, okay, are going to be this displacement over, or this displacement due to the F, right, over L1. And they're both compressive. So both of these are going to be negative because these are negative forces and these are negative. Okay. So in the end, we just add these two strains to each other, and that's what the strain in each section is going to be. Does that make sense? Yes, Andrew.
I didn't know that both of the deltas are going to the right.
Good question. In this case, I've removed the wall on the right. Okay. Right. So I mean, if it were like in space, it's got to expand, right? So like it's relative, right? So if I said, hey, I'm gonna think of this is gonna be my reference, then I'm expanding to the left. Yes.
And just to confirm, because there's a lot of talk about unconstrained and constrained.
Yes.
What you're basically doing with the geometry is you are removing the constraint so that you can see how much it wants to expand.
Yes.
And then you're putting that force back to see how much the constraint pushes against it so that it doesn't move at all.
That's right.
Okay.
Yeah, that's right. Okay, but in this case, that overall force is for the overall system, and then I have to take it down and to look at what's happening in the individual sections. Okay, so that's one way to kind of work on this, and if you do all the math out, all right, you can you get, yes, this epsilon 1 is equal to epsilon 1f plus epsilon 1 t, right? So this is the force, okay, that we have to use, the compressive force, and this is the thermal, right? And so this one is going to be negative, which it is, and it's a biggie, and this one is going to be positive, right? Because that force is compressing. But the net result, right, will depend on the values. Okay. What do I mean by that? Okay. You can foresee a situation where if you have a very stiff material, like a high E, right, and you have a very high thermal coefficient of expansion, say on the left side, let's say that the lengths are the same. Let's say that we've got, what am I talking about? Do I have space over here? I don't. Okay, we'll do it over here. Let's say that I have this situation. Can you read that? I have a very stiff material that also happens to have a very high thermal coefficient of expansion. In this push of war, which of these sides is going to win? They have the same length. Which direction will the middle go? Yeah, right? Because it's like, hey, I'm really strong. Again, I'm using the wrong term. I'm really stiff, okay? And I want to expand a lot, right? So I'm going to dominate you. I'm going to push you over, okay? And so that's what you're going to have. So the even though we solve this balance, right, which we saw on the previous slide, right? The overall epsilons are not. This is a different way to solve the problem. We'll go through it quickly. But you saw there was like a negative one due to the force, right? And a positive one due to the alpha delta t, right? Well, this is going to have likely a positive strain, okay? And this one on the right will likely have a negative strain, okay? Because it's pushing it to the right. So there are kind of these interesting balances, interesting things that we can think about doing here. Okay? Now, here's another way to approach the problem. Again, we have equilibrium, all right? And we have these kind of three pillars. We have I'm sorry. Okay, so the first, instead of using the fourth method, now we're using, sorry, I had it flipped. Now we're using geometric compatibility. Okay, sorry, I had it flipped. So like the first one was more like superposition, which makes sense, right? We have unconstrained and pushed, like Kira said. This one, we're saying, let's use the idea of geometric compatibility, which is that the deformation, right, of B over A is just going to be this alpha 1 delta T L1 minus F over K1. And the delta C relative to B is going to be alpha 2 delta T L2 minus F over K. This comes from this principle here, too. Or actually, now we're going to use this principle on top of it. Okay? Where the overall, right, displacement between A and C is going to be equal to 0. So then when we plug in these equations, all right, this is actually arguably a simpler way to do it. All right? We calculate the force, okay, and then we can calculate out the epsilon 1, okay, as delta B relative to A over L1 and epsilon 2 as delta C relative to B over L2. Okay? Still have the three pillars, but this is more using geometric compatibility. All right. Any questions on this? Yes, Andrew.
So is K1 the spring constant on the left and K2 is on the right?
Yes. Yeah. I'll try to keep us honest on the spring constants. All right, good, Andrew, good. Okay. Okay, so this is the assignment. All right, so we've talked about how to use finite element analysis, and we've talked about thermal strain and stress. Okay. Let's take a pause. If you want to stand up for a second, we're going to go ahead and move to the next section now.